So I wanted to come back to where we were in class Friday a week and a half ago, which was studying curves, and in particular how they can map into projective space. So we had sort of just gotten to proving that every smooth, proper curve is projective, a fact which you can extend to prove, for example, that actually every curve is quasi-projective. It's an open subset of a projective variety. Buckiel talks about how to do that. And in particular, on a smooth proper curve, every line bundle of positive degree is ample. So every line bundle we take, if we take a high enough power of it, we'll actually get an embedding into projective space. But we'll learn a lot more if we think carefully about the structure of curves. And in particular, what I want to focus on today is curves of small genus. So yeah, I'm always going to be considering a smooth. I don't actually need to say normal if I say smooth. Smooth and normal are the same thing for curves, projective curve. So there was this very important invariant of this curve called the genus. So there are various ways to think about this. It's the dimension of the first cohomology of the structure sheaf. It's also the dimension of the zeroth cohomology of this dualizing sheaf we defined. And we didn't get kind of into the details. I don't think we're going to have time to talk about differentials in general, but this sheaf has the property that its sections you can interpret as smooth one forms, right? You can sort of glue it together by using the transition laws you would get for smooth one forms. On a curve, this is pretty easy. You just use the usual transition maps for one forms that you learned on C. All right. And the reason that this is related to the genus, the other place that genus shows up is in the Riemann-Roch formula. And so, it shows up here. If I have any curve, then I get any coherent sheaf, a thicker line than that. If I have any line bundle, then I get that H0 minus H1 of L is 1 minus G, and defining G is the dimension of H1 of the structure sheaf is the special case of that for the structure sheaf. All right, so we've already seen that if we have genus equals 0, then what happens? Every degree 1 line bundle has to have a two-dimensional space of sections that defines a map to P1. That map to P1 is an isomorphism. In order to do that, I wanted to assume that my field was algebraically closed because I needed to find a point to give me a degree 1 line bundle. So if I'm G equals 0 and I'm over an algebraically closed field, or more generally, I have at least one rational point, then I get an isomorphism to P1. Of course, if my base field is not algebraically closed, there are genus 0 curves which are not P1 of that field. We've been mostly assuming that we're algebraically closed because it simplifies things a bit, but I think this is actually a worthwhile point to think about. So, for example, if I look at the equation x squared plus y squared plus z squared, so over C, that gives me a copy of P1 inside P2. It's the image of the two Upel embedding. But obviously that isomorphism doesn't work over R. There are no solutions to this equation over R, whereas a usual P1 has R points. So if you're working over an algebraically closed field, you have to think a little harder. There might not be a degree 1 line bundle that makes sense over your field. However, what you do have is you have the canonical bundle. That's defined for any field, and that's always degree 2. So on a genus 0 thing, that's always very ample, and it always gives you a map to P2. So this is telling you you can always write a rational curve over any field, no kind of issues about this, as the 0 set of a quadratic in P2. People would call this a conic section, or yeah. So I won't talk much about the non-algebraically closed case because it's, sort of opens a lot of cans of worms, but I thought this was sort of a simple enough application of it where you can sort of see what's happening, right? There's some quadratic issues coming from the fact that you might need to do some quadratic extension to get a point of your curve. All right, well, what about higher genus? Of course, we've talked about genus 1 many times, but I want to kind of come back to it. So if we think about genus 1, this is what's usually called an elliptic curve. People often adopt the convention that an elliptic curve is a genus 1 point with a choice of a base point, whereas a genus 1 curve is just a curve that has genus 1, doesn't have any extra structure. So on a genus 1 curve, well, degree 0 line bundles always form a group. They form a group under tensor product, but this is a particularly interesting case in which to consider it. On the other hand, if I have a degree 1 line bundle, that always satisfies that by Riemann-Roch, I have that the H0 minus H1 is 1. This H0 I can actually write as this H1 I can write as H0 of degree minus 1 line bundle. So by Riemann-Roch, I'm using Serre duality here, that H1 of a line bundle can be written as H0 of a different line bundle, which is the dual tensored with the canonical sheaf. So really what I'm writing here is LP dual. Oh, sorry, I wrote L here, but I really should have written O of P. You should take L equals O. So this is O of P dual tensored with this dualizing sheaf, but on a genus 0 curve, the canonical bundle is trivial. So by the definition of genus 1, it has to be degree 0. And by Serre duality, right, the structure sheaf has a non-zero section, a non-zero element of H1. So the canonical sheaf has a non-zero element of H0, and a non-zero section of a degree 0 line bundle gives you an isomorphism to the structure sheaf. I'm using Serre duality here. And what Serre duality tells me is, oh, this degree 1 line bundle still has sections of dimension 1. So this is something I had stated earlier in the class and told me you'll have to trust me. Now, using Riemann-Roch, we can see what the proof is, and Serre duality. All right. So what that means is this guy is not base point free, right? The structure sheaf has sections of dimension 1. This degree 1 guy has sections of dimension 1. So it's not base point free, and the unique base point is the point I added, where all the sections vanish. This is something I had mentioned before. So on the other hand, every degree one line bundle, again by Riemann Roch, has a non-zero section, and that non-zero section vanishes at one point because because of the definition of degree one, right? It's zeros and its poles add together to be a degree one divisor. There are no poles, so there can only be one zero. So we get a bijection between degree one line bundles and points. And this is a special thing about elliptic curves. This isn't true for higher genus curves. So we get a bijection between degree zero line bundles, which are a group, and degree one line bundles, which are in bijection with the curve, by choosing one fixed degree one line bundle and tensoring with it or tensoring with its dual. So adding P to the divisor or removing P from the divisor. And so what we find here is we get a bijection between C and a group, but only after we choose a base point, which is going to end up being the origin of the group structure when we think of it as a group structure on C. All right, are there any questions? So this is stuff I had kind of talked about earlier, but we can do things a little more precisely now that we have Riemann-Roch and can use higher homology.
I'm sorry, I guess I do have a question. So
Mhm.
before you said like so if we think about the canonical bundle, then at most like we have quadratic issues. Like
Mhm.
why is that true? Like for
Because
any
the canonical bundle has degree two. Um,
like
right? That somehow where this comes in is if you have there will be a meromorphic differential. There will even be a holomorphic differential. Oh, wait, do I have that right? No, sorry. Um, yeah, I want to get this right. Oh, I'm sorry. I actually messed something up. The canonical bundle has degree minus two. Um, So actually what we need to do, maybe I slipped this in somewhere, but I guess yeah, I forgot about this myself. I have to take the dual of the canonical bundle. So the dual of the canonical bundle, that's the space of vector fields. And the point is, so Riemann-Roch works over any field, um, but you have to be a little bit careful about degree, right? The degree of a divisor has to be weighted by the degree of the extension of the residue field over the base field, right? So if I'm working over base field R, I have to kind of remember that a point with residue field C is really kind of 2 points, right? When after I do the base change to C, it'll split apart into two complex points that are conjugate to each other. But over any field, I have a three-dimensional space of sections of the dual of the canonical bundle. I have a three-dimensional space of vector fields. And so I can use that to give me an embedding into P2 that's defined over any field. Right? It's a completely coordinate-free kind of thing. There's no choices. I just say I look at all the vector fields. I look at the complete linear system for this line bundle. That gives me a map into P2.
I see. Sorry, so like so can you give like one example of say like a irreducible cubic in some field? How do you write that as a quadratic? Like if you have some sort of irreducible cubic like in
I have
FP.
an irreducible cubic. Uh, sorry, you mean in two variables?
Yes, like
Why? I mean, I might just need to think about this more. Why do you think that that defines a curve of genus zero?
Oh, so can I like say like any
right? I mean, a
like
cubic in P2, a smooth cubic in P2 will define something of genus 1,
I see. Thank you.
right? For smooth plane curves, the genus is a function of degree. It's something like d minus 1 times d minus 2 over 2. I think that's right. Um, so for d equals 1 and d equals 2, I get genus 0. For d equals 3, I get genus 1. So this is like, we'll see in a moment, like why you usually write elliptic curves as cubic plane curves.
I see. Thank you.
Yeah, no problem. Yeah, I know. This is something very special. I mean, somehow the theme of this class is, the class today is that once you fix the genus, then you find out about a bunch about the behavior of the curve, right? Because what the genus does is it tells you about the dimensions of spaces of sections of line bundles. So as you increase the genus, right, Riemann Roch tells you it gets kind of harder and harder and harder for line bundles of small degree to have sections, right? For genus 0, they're forced to have sections. All line bundles of non-negative degree have to have sections, and they have to have, a bunch of them, the dimension plus 1. Um, on the other hand, for curves of very high genus, you expect to have to get, you know, kind of close to the genus before you have any sections other than kind of obvious ones. They're uh, as you add more points to your divisor, you get one section that vanishes on those points, but you might not get any other ones for a long time. Um, by the ampleness, eventually you get a lot of sections. But remember, we kind of did this calculation where every time you add a point to the divisor, you either increase the H0 or you decrease the H1. And so curves of high genus, the H1 is high, right? That's what you're increasing when you increase the genus. So you kind of have to fight through more dimensions of H1 before you start getting lots of sections. All right, great. Cool. Do, do, do. Right, so that's the sort of explanation of the group law on elliptic curves, which probably now I've talked about way too many times, but it's such a nice application of this story that I can't help myself. Now, what if we go to an elliptic curve and we think about a degree 2 um, line bundle? So, right, what we found when we went from degree 0 to degree 1, the space of sections didn't increase. So we soaked up that H1 on the, that the structure sheaf has. So degree 1 line bundles already have trivial H1. And you can also see that from Serre duality because their H1 is the H0 of a negative degree line bundle. So similarly, if I have degree 2, well, my H1 is already gone. I can't make more of it. So a degree 2 line bundle will have a 2-dimensional space of sections. Oops, sorry. So that 2-dimensional space of sections will give me a map to P1 over my field. Because my line bundle is degree 2, this means that if I take a point in P1, its pre-image will be a divisor of degree 2. Right? So somehow what you should think about is kind of as I move my point around P1, my divisor in the elliptic curve is going to kind of continuously move around as well. And it's going to give you the 0 sets of sort of all my different sections of the line bundle. This is kind of a good example to think about this sort of correspondence between the linear system and the map to P1, right? What this is telling me is I have two independent sections of this line bundle, and an element of P1 tells me like the linear combination of them to take up to multiplying by a scalar. So the preimage of a point on P1 will be the zero set with multiplicity of that linear combination. So most of the time, that's going to be the sum of two different points. But there's one other possibility for a degree 2 divisor. It could be a single point times 2. In that case, what's happening is my map ramifies. Locally near a point, it sort of looks like the map from C to C where I send Z to Z squared. If you want to think about this in terms of the local rings, this means that the generator of the maximal ideal in a local ring on the curve gets sent to the square of a generator of the maximal ideal in the ring on P1. So yeah, these are the points where L, right? L I can write as the line bundle corresponding to all of these different divisors, right? When I have a big space of sections, what I get is a bunch of different divisors, and L is O of all of them. So in particular, L is O of P2, 2 times P. One nice way to think about this is we can think about it in terms of the group structure. So what would it mean that the line bundles O of 2P and was congruent to O of 2Q? That would mean that the structure sheaf was isomorphic to O of Q minus P twice, right? Sorry, I didn't do that very well. 2 times Q minus P. So that means in the group of degree 0 line bundles, Q minus P has degree 2. Order 2, sorry, no. Has degree 0. It's degree 0 line bundle, but it has order 2 as an element of that abelian group. So when I think about P as the identity in my elliptic curve, Q becomes an element of order 2 in the group structure. And if you sort of remember that an elliptic curve looks like two circles, I get 4 points, which are either the identity or order 2, coming from the fact that in every circle, there's the identity and 1 point of order 2. You can also prove this kind of algebraically. Vauquil gives a proof using this hyperelliptic Riemann-Hurwitz formula, but I don't think we're going to have time to get into that. So if you want a more kind of algebraic proof, you can look in Vauquil. Are any questions? So yeah, this is yeah, okay, I decided to say a tiny bit about this. Because it's a degree 2 map, this means that the function field of my genus 1 curve is a degree 2 extension over P1. So how you sort of think about this Riemann-Hurwitz formula is I think about this quadratic extension of fields. And then I kind of analyze what's going on here. So in general, if I have an extension like this, what I'm going to get is that my curve has genus G if F has G plus 2G plus 2 roots. And when this happens, the curve is called hyperelliptic. So every elliptic curve has this form with 4 roots of F corresponding to the 4 points that are either the identity or order 2 in the group structure. But I can make higher genus curves this way. And we'll see in a moment, we've already seen that G equals 1 has this structure. That's why they're called hyperelliptic. All genus 2 curves have this structure, but then once you go to higher genus, you get it's a sort of special property. Most curves won't be hyperelliptic, but there's sort of a few special ones which are. If you think about sort of the space of curves, which maybe we'll think about a tiny bit, it's sort of a proper subvariety in there. One sort of famous way of studying elliptic curves is that actually you can determine what the elliptic curve is up to isomorphism by what these points of ramification down in P1 are, right? So if you look at this formula, you can sort of say, oh, if I fixed what the roots of F were beforehand, then I could build my elliptic curve just using this equation. Now, there's an obvious sort of symmetry here, which is P1 has a bunch of automorphisms. So P1 has automorphisms. Here I wrote an example of one of them that are given by, they're often called fractional linear transformations. So if I have A, B, C, D, an invertible matrix, right? That induces a map from K2 to K2, which sends lines to lines. So this induces a map from P1 to P1. And actually, if you sort of think about this line bundle story, this tells you that all maps from P1 to itself come this way. If I have an automorphism of P1, a degree 1 line bundle has to pull back to a degree 1 line bundle. So my map from P1 to P1 has to come from choosing two sections of O of 1, which is choosing an invertible matrix. So when I sort of write P1 as C with one extra point, these become what are called fractional linear transformations, which you've probably seen at some point beforehand. A famous theorem is that for any 3 points on P1 that are distinct, there's a unique fractional linear transformation that sends A, B, and C to 0, 1, infinity. You just sort of think about that. You write down the formula, right? A has to go to 0, so the numerator must involve x minus A. C has to go to infinity, so the denominator has to involve x minus C. And then you just fix that B goes to 1. So if I want to determine elliptic curve, I have 4 points in P1, the 4 points that it ramifies over. And I can apply an automorphism of P1 to send 3 of those to 0, 1, infinity. And then the 4th one goes to some element of P1 that isn't 0, 1, or infinity called lambda. All right, so this lambda uniquely determines my elliptic curve. So that's really good, right? You're tempted to say, okay, great. I have a bijection between elliptic curves and points in P1 other than 0, 1, and infinity. And that's not quite right, because I had to decide which ramification point was which to make sense of that statement. Right? I had to decide kind of which one was the origin, was the identity, which one was, I had to sort of name them A, B, C, and D. So there's a way of kind of thinking about elliptic curves with this choice, would be called a level structure of level 2. But we can also think, okay, well, actually, how non-unique is this lambda? Well, you have to think about, what if I swapped around A, B, and C? And what would happen if I swapped D with something else. So hopefully I've gotten the full list here. I'm not going to go into this in detail. Again, this is discussed a lot more in Vakiel, but you can certainly see, oh yeah, there would be different things that corresponded to the same curve. So for example, right, if you want to swap 0, A and C, you take the reciprocal. So 1 over lambda and lambda give you the same elliptic curve. If you wanted to swap 0 and 1, you would send x to 1 minus x. So 1 minus lambda also gives me the same curve. And then you start doing combinations of these. So these guys all correspond to the same curve. And there's a famous way of sort of getting around this, which is taking this thing called the J function. And there's sort of a long discussion in Vakiel of like why this is the right thing to do that will take all of these inputs and give you one function that sort of remembers what lambda was, but up to all of these symmetries. So if you study elliptic curves, this is something that will come up a lot, sort of thinking about this J function as characterizing what your elliptic curve is. And so two genus 1 elliptic curves over an algebraically closed field are isomorphic if and only if their J function is the same. All right. Oh, yeah, Jack.
Hi, sorry. It's just I'm not so like by invertible matrices, do you mean just the SL or the whole GL?
I mean the whole GL, but of course, scalar matrices will act trivially. So you'll often, right, there's this guy called PGL2, which is GL2 modulo all of the matrices of the form lambda, lambda, right? Because those will act trivially on P1 because they send every line to itself, right?
Is
But you
that
want the full GL2
right?
because you have a map that comes from, right? If you think about O of 1, you identify O of the sections of O of 1 with K2, and then you have to map that to the same thing, to K2. So that's an element of GL2. If you're not careful about what field you're working over, there might be the map from SL2 to PGL2 might not be surjective. I think that's right.
I see.
So it's kind of natural to work with all invertible matrices, but then to remember you actually have this symmetry, or this redundancy would be a good word for it. Are there any other questions? Right, great. So, I swear I'm almost done with genus 1 things. There's sort of one more, you can keep going, but there's one more sort of particularly important degree to consider, which is degree 3. So what Riemann Roch tells us, right, the degree 2 ones, they definitely weren't very ample. They gave me a map to P1 and that map was not an isomorphism. But by Riemann Roch, once I get to degree 3, then I'm very ample. So in particular, one obvious way to cook up a degree 3 thing is to look at 3 times a single point. And again, if you sort of think through this whole story, you'll see every line bundle of degree 3 can be written as 3 times a point over an algebraically closed field. That I don't believe that's true if your field isn't algebraically closed. All right, so what does that mean? That means that I'm going to take this degree 3 line bundle. It's going to have a 3-dimensional space of sections. So that's going to give me an embedding into P2. So again, we see we're getting a cubic in P2 because of the degree 3 part. So 3P is the pre-image of a hyperplane. That's telling me when my C is going to be cut out by some polynomial in P2, and when I restrict it to a hyperplane, which is a line, it has 3 points where it vanishes. So that's what tells you it's a cubic. Just as the degree 2 line bundle sort of gave us an interesting interpretation of degree 2 points as the ramification points of this map, degree 3 line bundles give us an interesting interpretation of degree 3 points. So what we're going to find, right? What is this telling us? That the pre-image of a line is 3 times a point. That's telling me my curve inside P2 intersects that line with order 3. So it's an intersection that looks like the graph of x cubed. So that's called a flex point. So there are going to be 9 of those because there are 9 points which are either the identity or have degree 3. If you don't have characteristic 2 or 3, then there's sort of a natural change of coordinates you can do. Again, it's discussed in Fakil, to get rid of all terms other than y squared, x cubed. I'm not including the z here, x and the constant with z added and to homogenize it. So this is the sort of familiar form of an elliptic curve you're most likely to have seen. This has the nice property that the map to P1 is forgetting y. So in particular, the 4 points of the ramification are exactly the ones where I'm on where y is equal to 0. And because that's exactly when you have only one pre-image, whereas if y is non-zero, I have 2 pre-images from taking the square root. So that sort of gives us this familiar picture of an elliptic curve like this, right? This is sort of the real points. So the points of order 2 are the intersections with the x-axis, and then there's one more I can't see because it's at infinity. So there's a point at infinity, which actually corresponds to this vertical line, which also has order 2. And the order 3 points, well, again, there's one at infinity, and they're a little harder to see in this picture. Some of them might actually be complex and so not visible here. But there are flex points where it's the points where you can draw a tangent through the curve, and the curve still ends up on opposite sides of it. Because that's what the graph of x cubed does, whereas the graph of x squared stays on one side of the line. All right, are there any questions? Hopefully we've now done genus 1 to death, but it's sort of, it's kind of a beautiful picture. And I do think it kind of illustrates how using this perspective of, thinking about the curve as an abstract thing and then trying to find the embeddings into projective space by looking at line bundles and looking at their behavior sort of helps.
Sorry, I guess so I just want to, so like, does it make sense to like say like define some function and say they are the modular forms in this sense? Like,
So modular forms show up here. So one word I didn't say here was line bundle, right? So this is slightly outside my area of expertise, so I don't want to say something wrong. Modular, so what's happening here is the J function tells you that the moduli of elliptic curves are essentially a rational curve, right? Essentially a copy of P1. And if I remember correctly, the like modular functions are either functions or sections of line bundles on that moduli space. So the sort of usual picture for them comes from a different way of thinking about elliptic curves. Right? It comes from this picture of I look inside C, I look at 1, and then I look at some other complex number, and I get the elliptic curve by modding out by the action of those elements. That's a sort of transcendental thing that doesn't make sense in the kind of algebraic geometry we're doing. That's really a like complex differential geometry story, thinking of the elliptic curve as a Riemann surface. But then you can think about this Z as being in a certain domain, right? There's an obvious symmetry where if I take a Z that spans the same lattice, then I'll get the same elliptic curve. That's an action of SL2Z that tells you all the different choices of Z that would give you the same elliptic curve. So I can choose Z. There's this sort of famous fundamental domain for SL2Z, which is like a kind of ribbon up to infinity above a circle. Um, let me make a new page. So, right, there's this picture you might have seen where you have a domain like this. That's a fundamental domain for the action of SL2Z.
Right.
And you can think about the points in the quotient by SL2Z as indexing elliptic curves, and the modular functions are sections of line bundles on that quotient.
I see. Sorry, I was thinking of something much simpler, like in classical theory of modular
Mhm.
forms. Like you can see the J invariant, I think is the first cusp form. That means like all modular forms of weight 0 are precisely the rational functions of the J invariant. So can
Yeah,
we do something like that here?
like that where, I mean, right,
Like we have the
exactly what you're doing is you're doing this transcendental operation, and then you're right, you're thinking about J as a function of Z.
right.
Right? And this thing about everything being a rational function in J, that's exactly, I have a P1 and J is the coordinate on it.
I see. Oh, I see.
Yeah, no problem. I mean, elliptic curves are sort of deep and beautiful story, but I think this story, I think this is a kind of transcendental story. Um, I don't want to, yeah, I don't know enough about this to like not start saying wrong things if I try to explain it. We can always
Thank you.
talk about it some other time. All right, well, we're pretty low on time, so let's try to say a little something about higher genus. So higher genus behaves very differently from genus 0 and genus 1. Again, if you know a little differential geometry, that might not be surprising, right? If I look at two manifolds, the sphere and the torus are very different from all the higher genus two manifolds. Um, if I want to think about this in terms of algebraic of differential geometry, I would say, oh, the sphere has a metric of positive curvature, the torus has a metric of zero curvature, the higher genus things have metrics of negative curvature. Obviously, that doesn't make sense in algebraic geometry, but you get this sort of similar manifestation of extremely different behavior between these three different cases. Um, In particular, one of the things that often happens is, oh, there are things you can talk about for higher genus curves that just don't work properly for genus 0 and genus 1. So one of these is you can consider this canonical bundle, the one forms. And for genus 0, as we discussed, I messed this up. I should have dualized and didn't. The canonical bundle has no non-zero sections, and it doesn't give you a map at all. In genus 1, Well, it has one non-zero section. It's technically base point free, but it gives you a map to P0. It gives you a map to a point. There's only the constant section. Whereas in higher genus, thinking about this map coming from the canonical bundle is very useful. The canonical bundle is always base point free. You can see this using Riemann-Roch. This is sort of dual to the fact that if I'm not a rational curve and I add a point, I won't get any new sections. So I get a map from the curve into PG minus 1. Now, it could be that my map is not very ample. Kind of generic behavior is that this canonical bundle is actually very ample, and I actually get an embedding from this map. But there are cases where I don't. So in what cases would I not? Well, as we discussed, you can test whether a line bundle is very ample by removing a degree 2 divisor from it, removing 2 points from it, and seeing whether the number of sections drops by 2. So if it always drops by 2, that means you're very ample. If there's some pair of points where it doesn't drop by 2, that means you're not very ample. So what would that mean? That would mean that I removed 2 points and I got a G minus 1 dimensional space of sections. When I apply Riemann-Roch and Serre duality, that's telling me I have a degree 2 divisor where the space of sections is 2-dimensional. So that tells me I have a degree 2 map to P. So it's sort of a cool thing that you can recognize these hyperelliptic curves, the ones with degree 2 maps to P1, that then we can say how many points they have to ramify over, if and only if this canonical map is not an embedding. If G equals 2, if you just think about the numerics, right? If G is equal to 2, then this guy has degree 0. So in particular, the structure sheaf, which is the identity of the Picard group, the structure sheaf is going to satisfy this. It's going to have 1-dimensional space of sections. So when I write my canonical bundle as in terms of 2 points, yeah, I'm gonna. Right, if you think about this, this is the genus 2 property tells you that the canonical bundle has a dimension 2 space of sections, so it gives you the map to P1. That's probably what I should have said, right? We're getting a map to G minus P of G minus 1, so if G is 2, we get a map to P1, and we're hyperelliptic. On the other hand, if G is greater than 2, then usually it's an embedding. Hyperelliptic curves exist. There's one for every, tuple of 2G plus 1 distinct points in P1. But that's not sort of most curves. So maybe the final thing I should mention, I'm out of time, I should quit, is that what does the space of curves mean? What am I talking about when I try to say that, oh, hyperelliptic curves, that's kind of not generic behavior. So you can imagine this by kind of thinking about families of equations. You have some equation for your curve, you kind of think about the parameters in it as variables themselves and think about varying those parameters. So ideally, what would happen there is you could say there was some scheme whose points are the curves, right? And we sort of saw that for the elliptic curves. It's very boring for genus 0 curves. You just get a point. For genus 1 curves, we actually found there was sort of an interesting moduli space, this P1 coming from the J function. For higher genus curves, it's way more complicated. I should maybe say we can also think about how to do this in genus 2 because they're all hyperelliptic. They come from choosing 6 points in P1 up to this symmetry. So you can imagine there's sort of a space, which is the space of such choices modulo the symmetry. Now, in general, it would be very nice if we could, for every genus, say, there's a nice scheme whose points over a field correspond to curves over that field. Life isn't sort of that nice. Saying, I want to do this. What would that scheme look like? Let me try to come up with it, is exactly how you end up thinking about stacks. So you sort of try to cook this up and you run into this problem that curves have automorphisms. So somehow a curve with an automorphism is going to be a kind of strange point in this space of curves. Now, rational curves, genus 0 curves, and genus 1 curves already have a ton of automorphisms, right? We saw the genus 0 curves, we have the action of PGL2. The genus 1 curves, we have the action of the group, the curve itself as a group. So they have tons and tons of automorphisms. Higher genus curves will only have finitely many automorphisms. And that number will vary. Most of them have no automorphisms, and then you'll hit some special one that does have some automorphisms. And so you need some sort of thing which is like a scheme, but where I keep into account that the points might be objects themselves and have automorphisms. And this is how you end up in the theory of stacks. I won't say anything else about that, but stacks sort of come into the game precisely because when you want to solve these problems, like, well, what kind of thing is the space of curves? You have to account for curves having automorphisms. All right, I'm out of time. Are there any last questions? All right, great. Then I will see you all on Monday in Waterloo in the usual room at the usual time. All right. Oh, stacks are the best. Well, maybe from one perspective. You'll probably get a difference of opinion on that about
Um,
whether stacks are in fact the best.
so I guess a natural question to ask is that why do you stop at stacks? Like
Why do I, well,
I
you mean
mean,
why do I stop or why do people stop?
yeah, why do people stop at stacks? Is that because they're uncomfortable working with three-dimensional category theory? Or
Um,
or
All right,
is
let
that
me address Roger's question first. Roger is asking, is there a lecture on Friday? There is not a lecture on any Friday. There are no future lectures of this course will be on Fridays. There will be a lecture on Monday and a lecture on Wednesday. Sorry, I did it today in part because I can't do it on Friday. And so, yeah, both this coming Friday and the Friday after, there will be no course. The Friday after is Good Friday, which is how we ended up with this slightly awkward course today. And sorry, to get to your question, Jack, I mean, generally people try not to use more crazy structure than they need, right?
right?
So stacks are sort of enough to solve the problems that people who were thinking about them wanted to solve, and they didn't want to add another layer of craziness to make things more complicated. Of course, like now there are plenty of people who think about like infinity stacks.
Right. So I guess it's just that I don't see why the space of curves is a good thing to think about, but the space of stacks like is not a good thing to think about. Like I don't see.
I mean, right, what does a good thing to think about mean, right? Like people have a lot of questions about curves that they want answers to. And thinking about the moduli space of curves is a way to answer those, right?
Right.
Um, so, I mean, I think a lot of this is just people don't feel the need to kind of create additional generality. But I mean, there are people who decided they did want to, that they should do in like infinity things, right? Uh,
Right.
there is a community of people who think about that. Um, I mean, honestly, I would say probably most people think the benefits of that perspective have not outweighed the costs of having to learn it. Um,
Yeah.
but opinions differ. Some people really like that stuff. Um, this is almost sort of a sociological question about like how do people decide that mathematical problems are interesting and decide that like a theory is a worthwhile investment of their time to sort of figure it out, right?
Mm.
Um, and there are various, there's always something new, that's some new way of thinking about things. And sometimes those things are hugely beneficial, and sometimes people ultimately decide, okay, well, there's some set of people who are going to be interested in this stuff, but it's not really going to affect the rest of us, right? That like, um, in 1960 or whatever, right? There was some graduate student in a classroom being like, "Oh, why don't we think about all this stuff in terms of categories?" And they had a good point. And maybe in 50 years we'll think of infinity stacks like we think about categories. I'm not so sure, but it's hard to predict what people will decide is kind of a basic tool, right? Um, this makes me think of there's this sort of perspective on things most identified with Peter Schultz of condensed mathematics. And it might be that in 50 years, we all think we should have been doing condensed stuff all along. But it's going to take a while before people kind of decide, like, is this kind of the way we want to think about things? What are the benefits of thinking about it this way versus just kind of the difficulty of switching to a new kind of mental firmware?
Thank you.
Hmm. All right. Any other questions? All right, then I'll end the call. I'll see you on Monday.